IffyQ, good morning.
Hey, good morning, Doug.
Pretty awake, splash a little water in your face. 20 ounces. Yes. Turn off my funeral. See. All right, everybody fill up and running. I saw a bunch of you jumped into my open math. That's awesome. I spent a considerable amount of time after class yesterday fixing all of that so that it's awesome for you. Just to make sure you see all of this, highlight it. I went in and I made a folder called course information. The syllabus is in there. The formulas I showed you yesterday, I stuck a derivative table in there, an integral table, and trig identities, just to have those handy in case you need those for something. After class, as I promised, I posted all of the notes from yesterday. So there's the writing that I did, and then I gave you a couple examples. There's that, and then the Zoom lecture. So again, if you miss a class or want to watch something a second time, that stuff will always be in there pretty much right after class. And then I got out my iPad and scanned all of the sections in the book, since, as I mentioned yesterday, I screwed up and sent you the 6th edition of the book. I'm assuming all of the sections are the same and so forth, but when you do your homework, don't do it out of the 6th edition. It's the 8th edition question. So inside here, this is yesterday's assignment, if you will. This is all the questions out of 1.2, whatever those questions were, I forgot. Is that clear? Is that cool? I think we're good there.
Yep.
So anyway, that should all be in there. Please hit me up right away. I work pretty hard not to make mistakes, but I make them. So today's, you may have noticed on your syllabus that today's assignment, I just didn't like the questions in the book, so I made a note to myself to make my own up, and I did so, and they're in here. And we are going to look at this a little bit later, but the questions are kind of down here at the bottom. So anyway, that's all in there. Awesome. So let's get after it. Cheyenne is here. Did I miss you yesterday, Cheyenne? I didn't see you. I don't think I saw you yesterday. Were you there?
No, I wasn't. I think I told you at the end of last term that Mondays and Wednesdays I may not be able to attend.
Oh, yeah. That's
but
right.
Tuesdays and Thursdays I should be okay.
Got it. Yep, I think you did. Thanks for reminding me. Awesome. Okay. Something awesome. So today we go toward a solution ourselves for a differential equation. We do not cheat in 1.2 and let someone else tell us the answer and wimp out and just check it for ourselves. We go get
I had a question about the homework.
Yeah, jump in. Thank you for interrupting again. I want you to do that every time.
Yep. I had a question about problem number 16. It kind of threw a few terms in there that I didn't understand, and I wasn't sure how to solve it.
Let's see. Yeah, I was a little concerned when I was a little concerned about the language behind some of that. 16. So let's see, what does it say? Verify that x squared plus cy squared equals 1. Let's see, can I just pull this up? No, not that easy. Yeah, if you can pull that up and look at it, just because it's kind of a weird question. Ideally, as I mentioned yesterday, since in the syllabus yesterday covered 1.2 and today we're doing 1.3, then I'm not talking about 1.2 anymore, except for questions you might ask. So my advice to you is always to try to do that assignment that night. Number one, just to kind of not get behind, but number two, because oftentimes, as you know, in math, maybe your understanding of 1.2 will determine whether you can understand 1.3, which we're talking about today. So generally speaking, that's a good move. So anyway, if you're looking at that question, it's the wording. This is exactly what I was talking about yesterday, the wording. So here's this equation, x squared plus cy squared equals 1. Notice that's not a differential equation because there's no derivative in it. But then it says where c is some constant, not 0. And they say it's a one parameter family of implicit solutions. Like, isn't that a complicated statement? A one parameter family of implicit solutions. What the heck is that talking about? Well, the fact that there's a C and not a C1 and a C2, that'd be 2 parameters. But there's just one constant. And because C is a variable and C could be 1 or 5 or 12 or -8, it's a family of solutions. And that'll make more sense today. There's a whole bunch of answers to this where C could be anything. And that's actually a solution. That's an equation. It's a solution to, oh yeah, this differential equation down below. So in a sense, it's actually no different. It's just saying, hey, there's this differential equation down there, dy dx equals xy over x squared minus 1. And today we're going to kind of try to solve those kinds of things. And then it's, hey, here's the solution, x squared plus cy squared equals 1. And they're saying, verify that's the solution. In a sense, it's no different than before. And so the fact that C can be anything, the example I did in class, C had to be like C1 and C2, if you remember, had to be -4/3 or something like that as a ratio. But that was a 2 parameter family of solutions. This is only one. It's just got one C. And so they're saying C could actually be anything and it will work. It doesn't have to have limitations. It can be anything and it will work in this. And then they're saying graph some of those solution curves. In other words, get onto Desmos. Notice it's not very easy to solve this for y, since it's x squared plus cy squared equals 1. Get onto Desmos and just graph that. Actually graph it just like it is with C and let C be a slider. And then graph, 3 or 4 different solutions. What's it look like when C is 2? What's it look like when C is 8? That's kind of the idea there. Did I say enough about that? I think that was David that asked the question.
Yeah. So
Right.
that made sense. I'll go put it in Desmos and see what happens.
Yeah, and for the most part, you should be using Desmos for lots of things in this class because we're going to be looking at really unusual equations. And again, that's an implicit equation the way they gave it to you, not explicitly defined for y, but implicit in the sense that it is sitting there, not solved for y, I guess. And Desmos likes those. And again, what we're about to do is going to add a lot of understanding to that statement. So good news is ahead.
Cool. Thank you.
Evelyn and I also had a quick question about
Yeah.
2b. We were just confused by why there is the phi of x at the beginning.
Yeah, isn't that weird?
Is that just like a way?
Yeah, again, unnecessarily confusing. Let's see. Let me see through.
I'm pretty sure that's just the book's notation for like a solution curve. So
Oh,
like
correct.
when they say, is this a solution? They're going to talk about phi. But that I don't know. That's just my sense from
Yeah.
It's the same as y of x.
right.
Okay.
Yeah. They should have said y of x. I'm not saying they're wrong, but they
Yeah.
just mean y of x. Because usually what you say is f of x. Like we've agreed that f of x equals a bunch of x's on the other side. It's just f of x is the same as y. Well, notice there's no f in that equation. Well, phi is just like f. It's just some letter that's out front. But you're right. It would have been much less confusing if they just said y of x. So
But Greek letters
y
look.
of x.
I guess so.
That's a good question. That's exactly what I'm talking about because this stuff, I can get you to understand this stuff really simply. So please never settle for, well, I don't know, the book example did it this way. I guess I'll do it that way. And like ask those kind of questions.
Doug,
go
how do you want us to turn in the homework for 1.3? So I finished the homework for the week and I already turned it in and I just took screenshots of GeoGebra and included
Yeah.
them in the PDF. Is that okay? Like with
Absolutely. Yep.
Okay.
Absolutely. I would prefer you use technology and we'll look at that a little bit today.
Okay. I just
Screenshots are good. You can
I just took
handwrite it
different
out.
pictures of curves going through the different points that you listed. So anyway, if it's not satisfactory, I could go back and do it again.
Yeah, no, I'm pretty lenient about that. I want to see your kind of handwritten written thoughts as much as possible. So that's great.
You want to see all my slope fields by hand?
No, I don't want to see slope fields by hand. I want you to not die of old age before you're done with this assignment. Cool. Let's see. Okay, that's not what I want. I want graph paper. There we go. Okay, so 1.3. And I could actually teach this to you in 15 minutes if we just wanted to like hustle and be done. But this is kind of a neat concept. I really want to take some time to kind of help you really get it. And maybe we'll even get done a little early, but this thing is called a direction, or sometimes a slope field. And I want you to think of this as toward, as I said out loud a while ago, toward a solution. We're trying to get our own solution. So for instance, if I said dy dx equals, just simply, it's a very simple differential equation, x over y. And we said, I wonder what, my computer's turning off again. I wonder what the solution to that differential equation looks like. And so again, what we understand, or what I'm hoping you're beginning to understand from yesterday, is that that solution is not 2. It's an equation. It's the solution might be something like y equals the sine of x. It's y is a function of x, or y equals e to x plus 2, or something like that. The solution's an equation. So we're trying to find some equation that will do that. That's the idea here. And today we take, in a sense, take the training wheels off, and we're not just given the answer to this. We got to go find it for ourselves.
Is the answer
So,
going to be implicit or explicit?
Don't care. Could be implicit or explicit. As long as it's an equation, who cares? Good question.
Are
So
we actually able to obtain a solution from a slope field that's not just visual? Like, are we able to get an equation?
absolutely. Yeah, absolutely. And so we're going to be able to move on from a slope field as a solution to these. But this is a really neat visual, and it'll help you understand kind of the power of what a differential equation can really do. And I got a lot of examples that I'll be showing you over the term. And so I want to do this slowly for a second anyway here by hand. And I want to make sure you understand how easy this is. We're going to quickly jump to technology to take care of this for us. But just as a for instance, and I mentioned this quickly yesterday, but let's just go to a point. If I said, okay, let's go to the point 2, 3, does it make sense that what you have in a differential equation, at least if it's solved for dy dx, is you actually have a way to find the slope? So if that's the point 2 over 3, then, or if that's the point x is 2, y is 3, then does it make sense the slope of that thing is quite simply x is 2, y is 3. Notice I don't have to do that much to it. I'm not squaring it. I'm not taking the sign of it. It's just divide them, 2/3. Okay, well, at that point, then the slope of our graph is 2/3. So I could actually make a little 2/3. So if I rise 2, run 3, if I want to be a little, it's like the slope right there would look about like that. You agree with that? Like, this is not hard. So I have no idea what this equation looks like. I have no idea if it's the sine of x or whatever. I don't know what it is. But at least at the point 2, 3, the slope is 2/3. Well, let's see. What's it at the point? I don't know, 0, 4. Whoops. Thank God for the undo button. What about 0, 4? What's the slope right there? Well, that'd be x is 0 over y is 4. That'd be 0. The slope is actually 0. So I could kind of put a little 0 slope right there. That's interesting. Here's a somewhat tricky question. What if I went to the point 6, 0? What's the slope right there?
Undefined.
Yeah, 6 over 0, undefined. How do I draw an undefined slope? Do I not draw one?
You give up.
It's really infinity. It's vertical. undefined as a vertical slope. 6/0 is infinitely steep. It's exactly what it says. Rise 1, 2, 3, 4, 5, 6, run 0. Oh, it's a vertical line. It's not complicated. So if I went to, well, this is interesting. Let's kind of speed up the process here a little bit. If that's true, does it make sense the point 1, 0? 1, 0 would also be vertical. 2, 0 would also be vertical. Like every place along here, all of those, -3/0, all of those are vertical. You don't need to know this, but one method to do this, instead of just jumping randomly around like I'm doing to start with, is to find all the places that have the same slope. Does it make sense? Everything on that x-axis would be something over 0, and therefore they'd all be vertical. Again, you don't need to know this, but your book calls this the method of isoclines. Well, for instance, then let's try to do that with 2/3. Like, where else would there be a slope of 2/3? What other points would you be at if you also had a slope of 2/3 like the point 2, 3 did? Give me an example.
Could you rewrite the differential equation with 2/3 substituted in for dy dx and then like get an equation for a line?
What's your thoughts on that? I'm not going to answer that, I mean, immediately. So David's idea is, could you just replace dy over dx with 2/3? So we're saying, hey, I'd like to know where every place on the graph has a slope of 2/3. Is that a good idea? Is that a dead end? Leads to death? Nothing's helpful there, or is that a pretty good idea? What do you think?
Would that then give you like a line that has the slope of 2/3 at all the points?
Well, let's see. If I wanted it to be a line, I would solve for y. So I could multiply y over to the 2/3 side, and then I could divide by 2/3. And so that would be kind of a better way to write it, or maybe a way that you're used to writing it. Let's let that question hang for a second. I'm just going to let it soak on you for a second. But somebody propose another point, another ordered pair that would also have the same slope of 2/3.
Would 4/6 be one? Yeah.
Yeah, 4/6 would be one, right? Where else? Think negative numbers a little bit.
-2/3.
Wouldn't -2, -3 also have a slope? Anybody have any thoughts on this now?
Yeah, so it looks like all the points are going to be on that line, that 3/2
Yeah.
line.
That's exactly right. So David's idea is actually pretty insightful. Again, that line is called an isocline. In other words, you can draw these lines through which all of the slopes are the same. And the idea here is kind of back when, cavemen were learning this and they didn't have the technology that I'll be showing you shortly. Machines, if you will, that will make these for us in 2 seconds, which is really fun and wonderful. The idea is you could speed the process up a little bit here by kind of recognizing where you'd have a bunch of places that had the same slope. Does that make sense? And so there's an isocline. Maybe I'll draw that in just because it's kind of fun to point that out. So but this isn't hard, right? Like this is really simple. This is not a difficult concept. So let's just fill in some other ones really quick. And again, I think we're only going to do this once. I'm not that patient. We probably should play around a little more, but let's see. So I don't know. Let's go way out here to. Now let's actually just start moving to the right. Like, what if I went? How do the slopes change? Like when I was at the point 2,3, it was 2/3. If I go to the point 3,3, then the slope is 1 instead of 2/3. If I go to 4,3, then it's 4/3. You see how it's getting a little steeper? Like as I move along, it's kind of hard to do this accurately, but basically as I move to the right, see how it's getting steeper and steeper and steeper? That kind of makes sense, doesn't it? And then if I'm here at 1/3, then the slope is only, it's a little flatter. And then when we get here, it's actually flat. So that's kind of cool. Do you see the pattern in that? That's not an isocline, but at least it's like, that's a better way of drawing these slopes, if you will, than just kind of drawing them randomly one at a time. What happens if I move over here? What if I move to -1/3?
Does it
Well,
just
now the
reflect along the y-axis?
Nice job. So the slope would be -1/3 and then -2/3 and then -1. And so it's actually going to reflect the way that I think Raymond said that is exactly right. It's an exact reflection over the y-axis, all the same slopes. And so that's kind of cool to see. So what happens if I sort of jump up? I jump up a level. Let's say I jump up now to the y is 4 lines. What's going to happen up there? Well, notice this slope was 1/3. Well, this slope here is going to be 1/4. It'll be a little flatter. And this slope here would be 2/4 or a half. And so they're all just a hair flatter. Does that make sense? Than the row below them, if you will. So there's definitely a pattern. Like if you're at some spot in space, then if you move up or down or left or right, it's going to change a little bit. So if I just think about, being here randomly, if I'm there randomly and I move down 1 to here, the slope, because the x just got, or the y just got smaller, the slope's actually going to be bigger. Does that make sense? Whatever this slope is here, I'll just draw it at about 1. This slope would actually be a little bigger because the y value just got smaller, right? X divided by y. If I move up here, it's going to get a little lower because the y value just got bigger. If I move left, the x value just got smaller, so the slope is going to get smaller since x is on top. If I move to the right, the x got bigger, the slope's going to get bigger a little bit. Does that make sense? So, I mean, you can play around with this. I want to grow your intuition here a little bit. I want you to have a sense of kind of how this works. Now, I don't remember that I posted this, but at least remember this vertical row here, because I didn't completely fill this in, and this kind of y is 3 row, because I'm about to just go to technology and let it kind of fill this in for us, because mine were approximations. And by the way, they can be pretty good approximations. Did you notice how I drew the slope of 2/3? I literally counted up 2/3, and so I had something to aim at. You can do a pretty good job with this even by hand if you wanted to. But of course, technology is going to just fill this all in for us kind of automatically and very quickly. And so let's play around with that and go take a look. So let's see, where did I put this? Was it here? That's not where I put it. Well, let's just go there anyway. So one place that will do this, for those of you that took my class in 253, you've maybe played with GeoGebra before, but one place that will do this automatically for you is GeoGebra. There's a couple of different places that this can be done. But GeoGebra is probably overall the best one. And notice on your assignment, I gave you a link up there so you can just click on it. Well, maybe I might have saved that as a PDF file. So let's see. Worst case scenario, let's see. I don't even think I can click on this. Copy. Paste. So you're seeing GeoGebra now, right? We're good?
Yeah.
Okay, so notice what it says over here, though. Let's stare at this for a second. I assume this is big enough that you can see it. Notice it says F prime parenthesis x comma y. Does that speak to you? Like, how come it doesn't say dy dx? Well, that is dy dx, like f prime. So in a sense, I wish it just said dy over dx, but it says f prime of xy, meaning the slope is a function of x's and y's. And when you look on the other side, there might be x's and y's over there. So does the language of algebra speak to you? That's just a different way to say dy dx. It's just kind of cooler in one sense because it doesn't have a fraction. And then it also tells you the slope depends on both x and y, not just x. So this is not f prime of x.
It's not parametric, right?
X and y. Say that again?
It's not parametric, right?
No. It's not. So I'm going to type in our equation, x divided by y, and there's the direction field that I get. Now, is that what we just did a second ago? Can you see that? Well, notice across the x-axis, they're all vertical. That's cool. Let's go up to the point 2,3. We did that one by hand, right? I'm at 2,3 now. Yeah, that's slope is 2/3. And then as I moved to the right, it got steeper, steeper, steeper. As I moved to the left, it got lower, and then it was flat, and then it was symmetrical on this side. Are you seeing it's the same? Except, bam, bam, done, accurate, 2 seconds. There's two things in here. Well, there's a number of things you might want to play with. One of them is you have control over the graph. Notice it says x minimum, x max, y minimum, y max. So I can make that larger. And then this density thing is really cool. You can actually kind of add the number of points. A second ago, let's see. When it was sitting there at a density of 11, does it make sense the ordered pairs that this chose were whole numbers, which is kind of what you would do by hand, right? What I was doing a second ago. You choose the 0.23 and the 0.87 and so forth. You're not going to choose x is 1.27 and y is 1.36 or something. But sometimes it isn't very descriptive. And so if you do this, can you see that now there's a lot more ordered pairs were chosen? And then you can even control how long those lines are if you want them to be a little longer or a little shorter to try to help see the pattern. Now, here's where it gets cool. And I said this on my sheet, but I'm going to click on particular solutions. And this is the whole idea behind a family of solutions. So we are literally seeing the graph of the answer to this differential equation, even though we don't know what it is. We're seeing the graph of it. So I'm going to turn one of them on. So if I chose the initial condition, you can't see that very well, can you? It seems really small to me. I stuck that at the point 0, 2. So A is at the point 0, 2. And if you chose that initial condition from yesterday, then that is literally the single one parameter answer. That is an answer to the graph. I don't know about you, but I'm thinking that looks like a parabola. But we are far enough in math that you shouldn't be quite that easily convinced. That might not be a parabola. There's a lot of other curves that kind of look parabola-ish. But that's one particular solution to this. But do you understand that these have a family of solutions? Can anybody put that into words? Why do these have lots of solutions, not just one? Why do they have an entire family of solutions and not just one?
Is it because of the constant? It could
Because
be
of the
any
constant.
number.
Where does the constant come from? How come a constant pops up in these problems?
When you integrate, you get that plus c.
Exactly. We have a derivative. To get rid of it, we have to take an integral. When we take an integral, we get a plus c. And that c could be anything. And the anything is what produces the entire family of solutions. And so if we said 0, 2 has to be an answer to this particular y of x graph, and we'll just say for a second it looks like y equals x squared, or maybe y equals x squared plus c. If 0, 2 had to be a solution, then this would be our particular solution up here. But that's not the only one. Notice there are some other ones. Like there's one down there. So let's stick that at a kind of a weird point. Oh, that's interesting. Notice at the point 2, -2, the solution is like a line. Isn't that kind of weird? Wait a minute. You're telling me there's one equation, a single equation that can look like a parabola and also a line? Yes. And it can also look like that. By the way, in that position right there, can you tell that's not a parabola now? Frankly, the top one looked like a parabola, but that's not a parabola now. I'm now sure. Can you tell it doesn't look right? Have you seen enough parabolas? Do you notice, and this is one thing that's kind of a bummer, do you notice it goes crazy in some positions? That's kind of a bummer. Can anybody tell why it's going crazy? Notice it's cruising along here just fine. Everything is looking great. It seems to be following the, well, do you notice these are following the slope field, if you will? This is cruising along, following the slope field, and then suddenly it just goes, wow, flies off the rails and, makes a big disaster. And then over here, it seems to like hop back on the rails and seems to follow it again. Can anybody tell where it's going wrong as I slide this around? Where does it seem to freak out and like lose it?
Is it on irrational numbers?
Is it on irrational numbers? That is a good hypothesis. Other hypotheses.
Are the slopes just too ambiguous to follow directly? Do they get confused or something? Like, does the curve get confused? The computer? I don't know.
Yeah, it's like the curve gets confused. And by the way, this is tomorrow's discussion. We're going to make these ourselves by hand using Euler's method. That's what 1.4 is about.
The curve.
But it's cruising along. Everything is kind of working great. It's cruising along here. And you notice what's happening right there? It's starting to get kind of steep. Well, that's the problem, is when it gets vertical, that's where it loses it, because vertical is undefined. And it basically is creeping along here. And then when it gets to vertical, then it just kind of loses it. And so the bummer about some graphs is anytime they have a vertical component to them, there are some of these that won't look right.
Are those still solutions to the
Yes, they are.
equation?
Yes, they are.
I wonder what that looks like numerically.
Yeah. Now I want to show you something cool. And to get this into notes, I'm going to.
Oh, quick question. I stepped away for just half a second, but so you might have said it. But are you able to get like, and I asked it earlier, but I'm not sure if I asked it correctly, but are you able to get like a y equals some kind of like solution from a slope field, or is it just like a curve that you can look at to analyze?
That's a great question. The only way you'd be able to do it is if you looked at it and recognized it. If you said,
Okay,
oh,
that's what I
that's
thought.
the sine of e to the x, I see that one, that's the issue, which is
Okay.
unlikely to happen, right?
Right. Okay, cool. Thanks.
That's a wonderful question. So I'm going to show you something else here now. Let's go back to my screen so I can write on it. Let's see, how do I do this? I can't remember, it's been too long. Photo library, there we go. So I just snapped a picture of this since I'm kind of writing on an iPad. So this picture will be a little bit lame, but it'll be better than nothing. Unfortunately, it's kind of cumbersome to do this on my iPad, so it's a little blurry, but you get the idea. So it's kind of cool to use technology to find particular solutions to this, but you can do this by eye and by hand. And so if I went over here, although it freaked out, if I started right here and I said, okay, there's my particular answer, notice that appears to be at the 0.44. And I say, okay, well, I'm just going to follow these lines. And so I'm following them down. It seems to be, actually that particular one seems to like stay right on there, doesn't it? It's almost like it's the line y equals x. Does that make sense? And to, I think, David's point, that looks like that solution is y equals x. But if I hop down here to the point 4,3 as my initial condition from yesterday's language, does it make sense? It sort of seems to drop off and then it curves. And I can't draw this accurately. You need to understand this. This comes down, it hits vertical, and then it kind of turns and goes back this way again. Does it make sense? That's what the computer was trying to do a second ago. It just can't do it because when it hits vertical, it freaks out and just can't do it because it's not solving these algebraically like we're going to do. It's just trying to trace along them. It's just trying to follow these lines. So I don't know exactly where that crosses the x-axis, but can you tell that's if I roughly follow those lines, if I kind of go in the direction those are trying to go, does it make sense? That's a solution. So I've got 4 solutions on there now of the billion of them that exist there. Let's add one more over here. So that this looks like it's curving down. It's about here, curves off. Maybe it looks something like that. So there's 5 solutions of the family of solutions to this differential equation. And so we're literally seeing, as David pointed out, we're literally seeing the answer. We're seeing the graph of this. The problem is there's only one equation there. Does that blow your mind? That's not 10 equations. You might look at this and say, hey, that looks like y equals x squared plus 2. And this looks like y equals x. Nope, there's only one equation there. There are not 10. They're not 100. They're all the same exact equation. That should both blow your mind and bother you simultaneously. What? How can that be? What are you talking about?
Do they just have different values for the parameter?
Yeah, they have different values for c, but that should bother you too because you think, you're changing a constant and it's going to go from a parabola to a line. There's no way that's possible. Like, you should be thinking liar right now. Now, this particular one is pretty solvable algebraically. And again, this is the discussion of 2.2, and I keep stealing my thunder by teaching it to you a little bit ahead of time. But I want to show you how kind of cool this is, because I think after today, this is going to give you a big understanding. But before I do that, I want to show you something else kind of cool. Scope this out. So I just went on the internet, found a bunch of pictures of stuff like this, but does your hair look like this? You got one of those on it? It looks like a hurricane. He's got hurricane here. But does it make sense? That's a direction field, if you will. I mean, that could be modeled by a direction field, a slope field. What's this? Can you tell what you're looking at there?
That's some airfoils.
Yeah, it's an airfoil. That's a wing of an airplane, and the sort of the direction that the air molecules would be taking as they, interacted with the wing. Notice the ones way up here are just a little bit bent because they're further away from the wing, whereas the ones that are, right here are radically bent. Like, isn't that what we just saw? We saw something that looked like this. This is one of the things that makes this so powerful, because we're looking for literally equations that model things like this. Well, in order to model all of those air molecules, does it make sense the answer to this, or the problem would maybe involve differential equations, because it's going to produce a direction field like this? How about that? That's a weather related map, if I remember right. I'm not exactly sure, but I think that's the case. And I think that has to do with the temperatures, like all the temperatures being the same at those elevations above. Notice they're really high, like 60,000 feet. I'm not sure. I made this so long ago, I can't remember now, but can you picture this as a direction field? Notice these particular points right here are really interesting. These nodes, they're called, later on we'll look at in this class, but notice you can kind of follow these crazy curves all the way through their big winding curve, and that would be one particular solution. And so, weather, you got to study differential equations if you're going to be a weather forecaster. Do you recognize this? Have you seen that before?
Is that like a contour map of like?
Yeah, it's a contour map. It's a topographic map. It's a way to show depth or height, like in a hill with a two-dimensional map. So again, can you see that as a direction field where you've just connected all the lines, you've drawn all the lines in? It's not a bunch just individual. It's not just individual little tick marks. It's you actually connecting them all, and not just drawing in 6 solutions, but drawing in 60 solutions. You might notice that the elevations go from 0 to -10 to -20 to -30. So what are you looking at there if that's the case? From the air, what are you looking at?
Some sort of gorge.
Yeah, it's a gorge or a hole or a depression in the rocks. It's not a mountain coming towards you. It's actually a hole. Does that make sense? That's kind of cool.
I think we're looking at level curves in calculus today.
That's exactly right. You're doing something in calculus called level curves, which is really similar to this. That's exactly right. Or maybe folds in a rock. A rock, that's kind of a cool rock formation. And, you know, magnetism does the same thing. Maybe you've seen a picture of magnetism before, but that does the same kind of thing. And so this is what makes this so powerful. So if somebody is studying this, obviously this is a good reason to study, you know, how a wing would work and so forth, and why that airfoil shape of a wing does the job it does. If you wanted to study something like this, it wouldn't be surprising if differential equations were required and knowledge of them were required to kind of understand that. Isn't that kind of cool and powerful?
So with the differential equation in the case of the airfoil, would it describe like the, so if it were like with position, would it be the flow then?
Yeah, that's exactly
the-
right.
Okay, and then the
And-
solution would be, if we were to pick like a coordinate there, that would be the solution curve would be the path that the particle follows. Then
That's exactly right. Yeah. And that's why there's a whole family of solutions. Because if you think of the air particles as all just hanging out, and then suddenly this plane comes flying through them,
right, you have to pick one and
you got
see
to
where-
pick a particle and say, what happened to that one? So you pick an initial condition, a certain particle, and, you know, how far is it away from the wing? And then it has its own pattern. If it's a different place, it has its own pattern. The amazing thing though is, do you understand that when you look at this picture right here, you're seeing all of the answers? That's what's so cool about it. You're seeing every
Right.
one of them. So if I go back and fill them all in, then that
kind of
models
like
a lot of things.
It's kind of like a graph of a differential equation. That's kind of cool.
Yeah. So you're literally seeing a graph of all of the answers. But you should look at this and say, how could there be one equation that actually models all those? Well, in this case, I chose a really easy differential equation because I actually want to show it to you. I want to go find it. So if dy dx equals x over y, because I spoiled some of my thunder yesterday, do you see that that's separable? Do you see that you can get all the x's on one side and all the y's on the other really easily? This is a really easy differential equation to solve. So if I multiplied, let's go down here. Let's go right here. Solution. Again, we're not supposed to know how to do this. The book is not showing you this. I just think I can't help but show you the bigger picture here. So if I multiplied y over to the left side and left dy over there, and I multiplied dx over to the right side and left x over there, do you see how it's really easy to separate those? And now if I say, hey, that's cool, I'm going to do the same thing to both sides and take the integral of both sides, that's possible to do that because all of the x's are on the right, all the y's are on the left. Well, you know what the integral of y is with respect to y. It's y squared over 2, or 1/2 y squared, plus c. You know what the integral of x is. It's x squared over 2, or 1/2 x squared, plus another c. And so I got to change these from c to c1 and c2. Now let's just think about this a little bit. Would you agree that before I could just go type that into Desmos right now and graph it? But before I do that, does it make sense I could subtract C1 from both sides? And now I have C2 minus C1 just to clean this up a little bit. So I could say 1/2 y squared equals 1/2 x squared plus, I guess I could call it some new constant, C3. Does that make sense? Like, why have two constants when I just need one? And then there's no reason for a half to be there. Couldn't I multiply both sides by 2 so that this becomes y squared, and this becomes x squared, and this becomes 2 times c3. But if it's a constant anyway, why not just rename it c4? Does that make sense?
Yep.
And so now that I'm finally kind of done, the easy answer to this would just be to say y squared equals x squared plus c. In other words, I'm not going to call it c4. Now that I'm done kind of fooling around with the constants, I'm going to call it just c. So there's your answer, my friends. That's all of those graphs, the red, the green, particular solutions that I gave. That's what you get if you graph y squared equals x squared plus a constant.
Is it okay to leave it implicitly defined, or are
Yeah.
you going to want it explicit?
No, I don't care.
All right. Well, if
And-
you want it that way, then you need to tell us.
Well, I'm just not going to say anything. So if you bother, not, and I would argue though that why is this a bad idea?
Well, in our original, well, because then that's plus or minus. You get two
That's
equations.
right. It's plus or minus. And so if you're using your regular TI 84 graphing calculator, you don't have a choice but to do this. But because of Desmos, you can actually type things in implicitly. If you type it like this, you're actually going to have a plus and a minus, and you're going to, in your graphing calculator, have to type 2 totally separate equations in. So I'm sort of on the lazy side in the sense that I'm going to stop when I can, but it's actually better to leave it alone. And you also understand that everybody could have a different answer to this. Like there's no reason the c couldn't be on the other side, y squared plus c. You could rewrite it as y squared minus x squared equals c, right? So there's a lot of ways to write it. I don't care. Like you should be algebraically strong enough to say, yeah, they're all the same. That's not something I'm nitpicking.
Cool. Good to know.
Good question. Now, stare at this direction field and memorize it a little bit. So there's that green graph up here that's a parabola. There's one solution. We got the line y equals x. There's one over here. Then there's like this parabola looking thing on the bottom. There's like parabolas kind of everywhere, like parabolas down here, parabolas over here, except they're not parabolas. Let's go to Desmos now, which I actually have an app for on my iPad, so I'm gonna have to switch to my computer. And I don't know why, but for some reason I want to graph it as y squared minus x squared equals c. I think that just seems cool for some reason. Notice it immediately says, which is so wonderful, add a slider, like c is a constant. Yeah, I want to add a slider. Bam. Is that the solutions we just saw?
Looks like
It is, isn't it? Notice it's every one of them. What happens when I go right there?
Is that a hyperbola?
I like the way you asked that question. Like, I'm not sure. It's like a conjecture. Is that a hyperbola? I remember studying this in maybe in Math 111 and maybe a little bit in Calc 3. The answer is yeah, that's a hyperbola. When you have an x squared plus y squared, that's a circle. When you have x squared minus y squared, that's a hyperbola. So notice when c is 0, it becomes y squared equals x squared, which if you square root both sides becomes y equals x. So do you see, isn't that cool how it actually is both? Again, I keep saying parabola just because I want to, but it's really a hyperbola. So the answers to this are actually all the hyperbolas. And there's one special case where the hyperbola actually drops itself into, bam, a straight line. But then notice when I hop into the negatives, boom, all of a sudden now I get the ones on the other side. And isn't that crazy? So there's one equation for every single one of those. I wasn't lying to you. That's unbelievable. So that's the family of solutions. Now, what's interesting is notice you kind of get a left and a right. Over here, you don't get a left and a right. In other words, if you said my initial condition is 4,3 and I want to know what happens to the particle as the wing flies past it at the point 4,3, this solution here is the only solution there was. It's not like it comes with the one on the other side too. That's
Right,
where
then
it would kind of travel.
Then it would be explicit because it would
Mm.
only be one of the halves of the.
That's right. That's exactly right. So if you sort of solved it for y, then you'd only get one of the halves. That's exactly what's going on there. Isn't
And
that
that's
crazy?
You can kind of see it where it's on the closer to the x-axis. It's like a parabola in the to the sides, and then when it's closer to the y-axis, it's more up and down or
Yeah,
open.
yeah.
I guess.
Very well said. Like up here, it's kind of flatter, and the closer it gets down, the sort of the sharper it gets. And
Right.
then you could see like right here, it's really getting sharp. And then you saw a second ago when I knew the Desmos, how if you get really close, boom, it just turns into that line right there. So isn't that amazing? Isn't that cool? So we literally have an equation that models the path of every one of the particles as it flies over the wing now. That's kind of the idea.
That's good stuff.
It's really good stuff, isn't it? And it's just really neat. You can see why this is such a practical, kind of a practical class. It's probably my single favorite class to teach for that reason. Let's at least throw this in the notes since it's so easy to do, so you can kind of study it yourself later. Again, this is kind of a neat way to check your work. That's kind of, this is kind of a really cool way to check your work. Crop, not cut. One of the things I always kind of like to just, I don't know, nerd out a little bit and think about is, the people that discovered this stuff didn't even have a pencil. We have a graphing calculator, and I'm sitting here kind of, mocking it as like, the graphing calculator is a piece of junk. Desmos is way better. And we have GeoGebra that lets us make a direction field or a slope field in 2 seconds for ourselves. And, just it's amazing to think of our ability to kind of conceptualize and play with this stuff in a way that, nobody in history has ever been able to do. Even Desmos is pretty darn new. Graphing calculators are about when you guys were born.
All right. Well, Desmos doesn't cost $100 like a graphing calculator.
Oh, that's so crazy and true.
I guess you have to have a computer though.
That's true.
But you
Yeah.
could just go to the library.
Yeah, it's a bit funny that I can still use my graphing calculator I got back in like 2005.
Yeah, it's
It
amazing.
was 3 years old in 2005.
You future educators have to think about how this works in culture. My overall philosophy is I am not here to be a policeman and police to make sure that you use the right technology or so forth. Like I want you to touch this stuff and play with it and so forth. And I hope to arouse your interest enough in this to say, why would I want to cheat? I want to understand this stuff. This is cool. I want to cheat. But that's something that educators struggle with is, how do you do this stuff when there's websites out there that just give you the answers to every math question you would ask? That's a tough one. So you future educators are going to have to figure out how you're going to do that. It's a tough one. Unbelievably cool. Well, let's just play with some more of these things then. Let's just play a little bit. Let's see. I got some examples here of cool ones that I've made up. And I'll write this one a little nicer. Y prime is equal to x squared minus 2y. So there's a differential equation. It's got a derivative in it. I wrote it in this form this time. This is not separable. Does anybody see? We can't solve this yet. You will be able to solve this, but we got to wade into this a lot deeper before you're going to be able to solve this one. You might initially think, wait, that's easy to solve. I can separate those. I'll just add 2y to the other side. We'll go down that road later. I don't want to do too much of that section now, but you're not going to be able to solve this one right now. I got to show you a bunch of stuff, but we can still make a direction field for it, right? Let's see. By the way, let's see. Actually, let's do this way. How can I do this really fast? I'm going to do this right now. Just it'll take a second. Just going to copy that link. I'm going to go into my email. I'm going to go over to this class. I'm gonna send you this link right now so you can play with this with me. I got to get it to you at some point anyway. So, and I think I sent it to you as a PDF file, which means you'd have to type the whole dumb thing in there, which is a waste of time. So,
The hyperlink worked for me when I did it.
link worked.
Yeah, it worked for me.
Okay, so you guys got it already?
I just Googled it a while ago.
Good. Okay, so we said the equation was x squared minus 2y, and you can appreciate that there really is, with technology, this is not complicated. There's really no reason to play very long with doing these by hand, right? Like I don't want you to do it for an assignment. I don't want you to do it on a test. Like, don't make a direction field by hand. This is too time consuming. So minus 2y. I'm gonna turn these solutions off for just a second. Let's see. So I play around a little bit with the density. Can you see the family of functions here? I don't know about you, but I find that a little harder. Let's see if I'm cruising from, say, right here, it looks like I come up here and kind of hit a turn and then it cruises down like this. And it kind of depends where I go, but it's kind of like it cruises over here. I'm not really sure. It's hard to see, right? And it's kind of neat to have these. So there's one solution. And again, do you see it is doing nothing more than just following those lines? I'll add more of them. Does that help to add more of them to increase the density? Let's see, what if I move this around a little bit?
It really seems to be converging to that one place on the right.
Yeah. Do you understand that statement? I like that statement. Do you see how this side doesn't seem to change? It's like converging to that over there. That's what your first project is about. Because I noticed that one day and I thought, wow, that's really interesting. Like no matter where you start over here, it's kind of like you end up over there. Isn't it interesting? See how the right side's not moving at all? Isn't that crazy? Like if I'm here, it's kind of parabolish, but again, you can tell it's not symmetrical, so it's not a parabola. And then if I get just a little too far over here, all of a sudden, bam, and it's, now it's kind of this cubic looking equation. Again, do you find yourself thinking, how could there be one answer to that? How could there be one equation that gives me all those answers? It's just unfathomable. How come this isn't freaking out? Like, how come the graph is working every place I go? How come it's not going crazy?
There's nowhere where it's undefined.
Yeah, it's not vertical anywhere. Notice if you're over here, it's like no matter what, it seems to want to exit the stage up here in the first quadrant. But over here, it's kind of a really boring path, right? It's kind of flies over there. But if I get over here, it's a crazy cool path that takes me where I'm going. And you can probably picture this as, it's kind of neat to think about space this way because that's how gravitation works. If you're flying through space and you're a meteor or something, you're just going to fly in a straight line unless you get in to the area where there's a gravitational field. So perhaps you could appreciate there's a planet right here. So here's this particle cruising along and all of a sudden it gets into the gravitational field of this planet and then it gets bent around the corner and then it would have headed back off into space in a parabola because that's how gravitation works. It would have curved in a parabola. But then when it got right here, it got near another planet that was even bigger perhaps. And then it got bent in this direction and then it took off in space from there. Isn't that kind of cool? I mean, that's what's so kind of powerful about this. It's no different than the air particle that got in contact with the wing because the plane flew by. Whereas this one over here, it's like it was never close enough to those planets to kind of be altered by them. This one up here never got in contact with that planet at all. It just got in contact with the one that was over here. And so in a sense, it models the flight of all things through space where there's like a planet here and a planet there or something of that nature. I mean, can you see the power of this? Again, I'm just trying to grow your conceptual understanding of this. So of course, what's kind of fun with this is to, do a whole bunch of them, like do them all at the same time. This lets you have as many as 4. And notice these aren't screwed up. So that's kind of fun. So there's 4 pretty cool graphs. And so what I just showed you, with the kids' calictare or the folds in the rock strata and so forth, all you do is just keep going. Like, don't just stop at 4, have 40 of them. And then you're seeing paths. And so, yes, every one of those, it's literally showing you the picture of an equation that is the solution to this differential equation. But unfortunately, like me, you don't look at that and recognize it. Like, oh yeah, I recognize that one. That's y equals e to the sine of x divided by natural log of x, or natural log of y, or something like that. It's like, these are way too weird to recognize. You get really crazy graphs. And that's because the real world is really complicated. Turns out this one has an x squared in it. It has an e to the negative 2x in it. And it has a lot of stuff in it. I do know how to solve these, and you will too later. And so this answer is really crazy. That's kind of fun. So, what's this section about? Like, there it is. Like, this section is really easy because I just want you to use technology. I want you to play, frankly. I'm giving you 2 questions at the bottom of your assignment, just like this. And I just say, show me some particular solutions to this. And by the way, I can ask for a very particular solution by just telling you to drag A to the right location. So if I say, I need the particular solution graphed of the equation when, in this case, notice it's y's and x's. So if x is 0, y needs to be 2. Now you have a particular solution, not just a family of all the billion different graphs. You have one, and there it is. And then give me another one where x is negative 2 and y is 0. There's another one. That's what your assignment is. It is kind of cool to sketch them, but can you appreciate how hard that is? Like, once the technology has done it, and again, I'm going to show you how to do this yourself tomorrow. Like, how does the computer actually get that perfectly green curve right there? It sort of seems to do a really good job of it. Whereas if I tried to sketch it, it's going to be terrible, right? I'm going to get off track. I'm not going to be able to follow it very well. I'm going to show you that.
Can we see what the constant is when you move it around? Can we see what number that gets set to?
I don't understand your question. Try that again.
So like in Desmos, we can have C and we can see exactly what number C is. Can we see exactly what number C is on this too?
Got it. So you want to see the answer to this?
I think
Yeah.
you would need it to be shown like a solution equation for that. And I don't think that this does that.
Yeah, this is not finding an answer. It's just showing you all the graphs. That's all it can do. It's doing it mechanically by literally creeping along one at a time. It's like, I located the 0.02, and then let's move a hair to the right and locate a new point. That's what I'll show you tomorrow.
Oh, okay.
And so I think as you move the curve around, what it is it's showing you what would happen if you were to alter the parameter. So
That's
value.
exactly right. So the point is every one of these is an initial condition. If I say the initial condition is y of 0 equals 2, that's the initial condition here, y of 0 equals 2, then the particular equation that you would get, where there's no c in it anymore, it's now a number, would give you this green graph right here. So that's the initial condition.
Okay.
And then
Oh, so
there'd
the
be no
slope
c in it.
field is like the slope field is like the general visualization of the general solution to the equation.
Exactly. It's the
Okay.
general solution, which is a family of solutions, millions of graphs that are all on the same screen. That's exactly right. And then
Right.
as soon as I say y of 0 equals 2, in other words, that's the particular particle we're interested in here. That's the location on that kid's head, or that's the location in the storm of a hurricane spinning around, that kind of a thing. Then we would have one particular solution to it.
Right. It shows you all the different curves at once.
Exactly. So this shows you every single one of them. It's a general solution to it, leaving C in it. And then that green graph I'm showing you there is one of the particular solutions where you can just pick C randomly and say C is 10. Or you can say, no, you have to go find C such that y of 0 is 2. And then, we'll be doing that later on. But this is just such a cool visualization.
Right. So you can't see C, but you can see the initial conditions.
Correct.
Cool.
So I don't think I have the solution to this written down.
You could solve it.
Yeah, you don't want to see that yet. You gotta know too many things for me to show you that. It's not very far away. It's not gonna be a month. You'll know how to do this pretty soon.
It's like next week or something,
Yeah,
right?
like next week.
First
That's
test.
exactly right. Mhm.
Because it's
Let's see. Let's see, let's just play around a little bit and do some other ones. What about x plus y? This also has a plus sign, just like the last one had a minus sign. This has a plus sign. We don't like plus signs, like they're not separable. Maybe I'll take a second and show you that. But can you see, again, all of them here? All of the answers a little bit. Can you kind of sketch your own curve right here and say, oh, okay, if I was up here, if I was at the point -3, 5, then the curve would be right about there. Yeah. So I'm going to go do that. -3,
like a
5.
vacuum cleaner. All
So
the points
there's-
in space get sucked up to that center.
Yeah. Do you see where they all, I like the way you described that as like a vacuum cleaner. Where are they all going? What's the same about all of these? Notice it kind of wants to be a straight line, but then if you get over here, suddenly it kind of curves the other direction. And again, if you want to see a little further out, then go change these. I'm going to go out to -10. And maybe you feel like, there's stuff out there. I'm not seeing everything I want to see. There's things going on out beyond my field of view. And so you say, I want to see what's going on out there a little more. Notice that actually helped, I think, here. Now I can kind of see it curving away. So again, one of my personal facets, I haven't seen anything written down in a book about this, but isn't it interesting that the right side of this graph kind of freaks out? But it's almost like all the particles are being sucked. I like the vacuum illustration that you used. It's like they're all being kind of sucked. They're all exiting the stage in the top left there this time. Last time they sort of exited the stage at the top right. This time they're all exiting at the top left. But again, radically different. Notice that if I pick this point super careful, I actually get the line y equals, looks like y equals -x, doesn't it? Well, -x minus a half or -1. Y equals -x minus 1. If I choose that carefully, like that particular particle's path was just straight off in space, whereas this particle's path was over here and then it sort of hit this and then curved up that way. And then this particle's path was curving along and then it left that way. But they all sort of exited the stage up here. Is that kind of cool? So that equation right there is called a linear differential equation. It's linear. Again, this isn't a very nice way to write it, but there's a dy dx on that side, which has a 1 in front of it. And then there's a y, which has a 1 in front of it. And then there's an x, that's linear. And so there'll be a way to solve that. So there'll be a section where we say, oh, now we're going to learn how to solve linear differential equations. And we'll be able to find this family of solutions ourselves. And then we can kind of make these graphs. But again, it's so amazing that you can actually model this and not really know anything. Like we're just drawing a picture of it thanks to technology. Really cool.
Yeah, and you can kind of deduce the nature of the solution based on what's going on. Like this
Yeah.
looks like there's going to be something exponential involved with some linear term maybe.
Yeah, notice it has kind of an exponential nature. It gets really steep really fast over here. And so you can start to kind of grow some intuition.
Right.
But what
but
you'll
it-
notice about these problems is they'll be like a parabola plus a sine wave or something. It'll be like x squared plus sine of x. And that's why it behaves so weird, because you have kind of two contributions being made. You know what sine of x looks like, you know what x squared looks like, but what's x squared plus sine of x? Well, that's a different animal. More going on kind of when you go down that road. For some reason, I find myself wanting to quickly look at that. Y equals x squared. We know what that looks like, but what if I say plus the sine of x? Notice that actually looks a little bit like what we just saw when we were over here. Looks a little bit like that.
Oh, it totally does.
But notice it, and I just made that up randomly. That was totally luck. But can you tell if you look at first glance, if I said that to an earlier algebra student, they'd say that's a parabola. But you can tell if you look closely, it's not symmetrical. maybe if I zoom out, I see some other kind of pattern to it. And of course, where this is really fun is if you throw some constants in front of things and, let it vary a little bit. You see how we're getting all the crazy graphs we're getting? And again, I just kind of quickly made that up. All I did is just add two equations together. It's not like I planned this. But you see how that's a family of solutions that actually, if I pick C to be 0, what's going to happen?
That was just x squared.
Now it is a parabola. Does that make sense? Because the sign that component just dropped out of the problem. And so if I let that become part of the problem, then I get into all these. So can you see that as a family of solutions? Like in my classes, I've played with Desmos a lot. So in a sense, you've already seen this happening. And of course, it's even funner if I go in here and throw a value in for K, because then you can let K be 0. What's going to happen if K is 0? Well, now the parabola went away and you just have a sine wave. So now you have like a sine wave, a parabola trying, it's like a sine wave trying to follow a parabola. I mean, isn't that kind of cool? So that's why you're not going to be able to recognize the answers to these things by looking at the graphs, because they're combinations of things. That's what you're going to see. So you're not going to be able to recognize them. However, I would say this probably does have an e to the x in it right there, because that's going off the stage really steeply, like an exponential would. And so I'm guessing this is going to have an e to the x. And so maybe over here, it kind of looks like a line. So maybe this is something like x plus e to the x. Does that make sense? Like cx plus de to the x or something like that. Maybe that's why this equation takes on the shape that it does. So I'm hoping you have a really good feel for the concept of a family of solutions now, and how one equation, by just changing some constants, can have a whole crazy bunch of different solutions. And notice these constants are not just added on to the end. If you add it on to the end, notice that doesn't do much. It just moves it up and down. But if the constant is multiplied by something, then it's making a lot more significant difference. Let's see, I have in my notes here that dy dx equals sine of x plus y cubed is an amazing graph. Sine of x. So can you see the family of solutions there? Sort of feel like I see it enough this time without the 10s, and so I'm going to go back and put 5s back in here. For me, it's almost hard. Like I'm starving to see like the lines curving through it. Does that make sense? Like, oh man, I want to see where those things are going. I can kind of see it, like over here, it curves up. This is kind of cool. Watch this, because this is kind of neat to see. You come up here, and then what happens right here? Well, notice some of the people sort of turn and go down, whereas if you're just to the left, some of them go up. Isn't that kind of cool? There's like a dividing line. There's like a fork in the road. That's where you are in your life right now. You make one tiny little decision, and then your whole trajectory of your life changes. So, where am I? If I'm right here, oh, what's going to happen to me? Am I going to go up or am I going to go down? Oh man, that's really interesting. And so this is kind of cool because of that division. Do you see that? I mean, is that kind of neat? So I find myself just starving to get, some graphs on here. How come I don't have any? Solution.
You got to zoom out more.
Yeah, it must be that A was left over from the previous screen or something, and it was too far out and I couldn't see it. I don't know what's going on there. So if you will, this path, veered off and it went to the right, and then it got in the gravitational pull of something else and it sort of exited the stage down there. Whereas if I move this, can you tell if I move this a hair up, this is just going to go up like that. So notice those went up that way. And so again, I find myself just thinking, wow, look at all these cool graphs. And again, I'm getting really lucky because notice I don't have any verticals again here. I didn't have any verticals, so I'm actually able to see them all. Do you see again how they all kind of want to take off over here? Like this is where they all want to go. But there's this cool dividing line. And that's one of the things that I'm kind of fascinated with is see how these kind of like these up here kind of wanted to leave. If you think of it as like coming into the screen from moving from left to right, this one ultimately it zigged and zagged in here, but it ultimately wanted to leave the stage toward the top. Whereas if I get down here just a little bit, all of a sudden, bam, it wants to go to the bottom. So where's the dividing line? Like, is that one going up? I need to see further to the right. Is this one actually turning and going back down? Or is it actually going up? I can't really tell, but I'm interested in what's the dividing line there? It actually kind of looks like a sine wave, doesn't it? It's like if your hair above the sine wave, it goes up. Hair below the sine wave, it ends up going down. So as I'm thinking about this as like a particle moving past the wing of an airplane or a meteor flying through space or so forth, or maybe something move, just like a particle moving based on gravitational field. It's like where it goes. This is kind of the butterfly effect idea. You're clear back here, and yet a tiny change. You see that over here? Like a tiny change. This guy went down, boom. This guy went up, and it's just such
I want
a
to know how to
teeny
model.
change. Isn't that kind of cool? Think about it that way.
Now I know. Now I want to know how to model all these things.
Yeah, I mean, don't you find yourself wanting to like, I don't know, like locate a couple of planets in space and say, okay, there's one here and there's one here, and this is how big they are. And now let's let stuff fly through them. Let's let a meteor field kind of fly through those, and let's like map out. Let's do all the math and figure out where everybody's going to go. A few years ago, when I was building the house that I live in, that was the summer that 3 summers ago that we had the solar eclipse in the middle of the day, and I just found myself, even though I know math, just thinking that's just so crazy that you hear about it in the news. And I mean, there were people traveling from all over the place to go in the Bend area because that's where it was going to be a full solar eclipse. And there was no motels and everybody was camped everywhere. And it's like people were renting their houses out for $700 a night over in Bend. And all of this was because the news told them there was going to be a solar eclipse. And, they all went out there, spent all this money. And sure enough, there it was, exactly the same day it was predicted. And it's because of, you guys. It's because of people that like math, that we understand. We're able to understand these things and how things kind of move through space. So it's kind of cool to think that you can predict things and model things, and powerful stuff. Let's see, where did I put this? I want to show you one other thing here. Can't find where I put it. I had a whole bunch of, I had two other websites that are places I found that give direction fields. I was trying to find like the best one. Where is that dumb thing? There it is. You guys see that right now, right? Can't remember what I shared.
See a doc, a Word doc.
Yeah, Word doc. So notice Desmos has a version for this. I'm just going to show you all of these really quick. GeoGebra has a version. Notice I said the solution curve goes off the rails when it reaches a vertical slope. So I'm warning you about that. Desmos has one. I'm going to go there right now. And by the way, this isn't. So this is not just plain old Desmos. This is some nerd writing a program in Desmos to do this automatically. I don't understand this completely, but notice what's really cool about this is, and by the way, notice this is 2x over y, which is almost the same one we started class with. It was x over y, and so notice it has the same look. But it has this kind of movable point, and you can kind of take it anywhere you want. And notice it shows you the slope in that area. So its slope kind of matches the slope. I like the fact that it's got colors in it because it kind of shows you those isocline ideas and how, as you move across the graph, it gets flatter, 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 and then it's flat, and then it gets steeper, steeper, steeper. But the one thing that's really terrible about this is you can't actually, it doesn't draw the line, it doesn't draw the curve in for you. But again, this is literally manually somebody drawing a bunch of teeny lines, a bunch of teeny equations. It's literally doing mathematically what we did at the start of this class. Like, okay, plug in a value for X and Y, and then graph a little teeny chunk of the line that goes through that point. You could find the equation of that line, right? If we said it went through the point 5,5, and so you went over here and went, okay, I'll put in 5,5. 2 times 5 is 10. 10 over 5 is 2. Okay, the slope is 2. The slope is 2 at 5,5. Yeah, that looks right. Looks like about 2. Let's drag this over there. Yeah, it looks like about a slope of 2. Notice it's aiming right there, which is up 2 over 1. Again, I want to just make sure you have no mystery to this. It's super easy. But then you say, okay, it has a slope of 2 and it goes through the 0.55. Well, isn't that the equation? Y equals 2x. What is that? Minus 5? 2x minus 5. And so then you graph just a teeny little chunk of the line 2x minus 5. That's what all of this crazy syntax is over here that some nerd took a bunch of time to figure out. So they made their own slope field. And then this movable point. How do I get that point to move? I can move it any place I want, and yet it draws like a teeny line for me. It finds the slope and draws a teeny line. And so that's kind of cool. That's kind of worth something. And then the cool thing here is, of course, I can just go in and make this anything I want. Let's try something really crazy. Like, what's the sine of XY? This is really what I want you to do for your assignment today. I'm asking you for a couple of things, but I'd really rather you just go play around. Like, go write the most crazy statements you can think of and look at your slope fields, and and start a class tomorrow, like share them with us. But again, I don't like this one very much because I find myself looking at this and I can't see where it's going. Like, I want those curves going through it so I can kind of see what's happening. So Desmos is kind of cool, but that's not that helpful. Let's see. This one's cool. Let me see if I can show you why. I found this one. This was like yesterday. I just started looking because every time I teach this class, all the links are broken from the previous times I did this. So if any of you are interested enough in this and go find one that's better than the things I've just showed you here, please share that with us. So this solution curve can be set up to stop when it reaches a vertical. In other words, it doesn't hit the vertical and then panic and freak out. So let's go there. That was the one that started class today, right? The one that started class today had the vertical in it. So I'm going to go back to that one. It was X over Y. So for instance, again, let's just stare at this so you kind of see and notice there's a bunch of other stuff in this that's going to get cooler later in this class. I've never seen this before, but we're going to solve a system of differential equations later in this class. Notice it uses some of the knowledge. ODE is ordinary differential equation. Here you can even mess with the variables and say, no, I don't want dy dx, I want dy dt, I want dx dt. I can control the size of the screen, and I can again control the segments and so forth. So that's the same graph we saw earlier, right? So if I want more segments, I want it to look better. Okay, so then let's pick a particular point. So this does that. So right here it says plot numerical solution curves. So I want to plot the one that goes through the point 1, 1, 2. I'm just making that up randomly and I say submit. So that's what we saw earlier, right? Not as cool, like the fact that I can't just grab that and drag it around. I don't think that's near as cool. That's why I showed you the GeoGebra one. It's the best one I found so far in my very little looking. I like math, but I don't like it that much.
Yeah. According to the website, it says you can click on the graph.
This one?
Yeah.
I can click on it? Oh, yeah. So I can actually just click points. So notice it's got some freakouts in it, but notice this one's better because I can have hundreds of these and not just 4. So that's kind of cool. Thank you for noticing that. Clear all curves. So if I stay up here where everything works nice, right, then I don't get anything going wrong, but as soon as I go over here, bam, doesn't work, right? Again, that's because, well, you'll see this tomorrow, but that's because it was cruising down right here. It got vertical and then freaked out, and then it just kind of didn't know what to do. It went off the rails and bounced everywhere. But notice what it says right here. It says Euler. Tomorrow's discussion, the title is Euler approximation. So how did they write a program that would do this for us? It's called Euler approximation. It's really simple. I'm going to show it to you tomorrow. But notice that's not the only option here, clear all curves. There's a bunch of these others. And this last one down here, Runge, Kuta, Felberg, those are probably people's names. I actually don't understand what this is. I haven't played around with it. But watch what happens if I say use that method. Don't use Euler's method, use this method. Watch what happens if we click over here. Isn't that cool? It basically went down here and it got to vertical and just said stop. Now, does it really stop there? No, it actually keeps going over here, but it can't reconcile infinity. So it basically is hitting infinity. It's hitting an undefined vertical slope, and then it just kind of goes, at least it stops instead of creating all that other stuff that really isn't there. And then I guess I could kind of click the other side of this here, and they're, together. Notice I missed it. There isn't exactly the same, but that's kind of what that side looks like. See what I mean? So that's kind of cool, because realistically, if you're in any of these other methods, it doesn't work. I don't want to see all those jags, because those are really not there. I played with this for 10 seconds the other day, and I don't know what all of these techniques are. This is somebody that's looked into this a lot more. Notice that's a little better, but it's like none of those still work. All of those freak out. The only ones that don't are the ones that say, when I get to infinity, I'm just going to quit. And so there's a lot of other stuff in here. I haven't played with any of this stuff. Numerical solution tables, how to use this page, how to enter expressions, plot other functions. Like I haven't played with any of that stuff. I found one, I can't remember where this was, but I found one that actually solved it for you. Not only did it say, here's your graph over here, but it actually said, here's the answer to it. It literally listed the y squared equals x squared plus c kind of answer to it that we got ourselves a minute ago. I can't remember where that was, but that's kind of a neat way to check your work. I don't think there's anything else I really need to say about this, and I don't want to start the Newton's method thing. We'll just, or Euler's method thing, we'll just save that for tomorrow. So I think we'll leave it there, except that the only other thing I just want to quickly this is what you guys see. I just want to quickly pull up tonight's assignment. So you have to go here for this one because it's not even a scan, because it's not out of the book. So you're familiar with this now, but the main thing is just the assignment. So notice I said a few things about it, but really all I said was, hey, here's a couple cool, graph these direction fields and solution curves through the given points. And so here's one cool one, dy dx equals xy over y minus 1. Here's another cool one, dy over dx equals x squared plus sine of y. And I want you to add the solution curve, particularly, like I want you to not just make a bunch of random solution curves, but give me these particular ones. The one through 0, -2, the one through -1, 1, the one through 0, 2. I think this one here has a vertical one. So there's actually one you're going to have to draw by hand, and the computer won't do it because it wants to freak out. But you saw that most of the time that doesn't happen. Like you don't have vertical slopes every time. And so lots of the time you don't have that issue. And so you can just kind of drag this around and get all the curves you want. And GeoGebra is awesome because usually 4 is enough. If I have 4, or even if I can just take one and drag it around to all the different locations, I can kind of see what's happening there.
When we turn in 1.3, do we just take a picture of GeoGebra?
Yep, you can take a screenshot of it in any way you want. You could take a picture of it right on your screen with your phone, low tech, and just send a copy of that. The only other thing I want to show really quick, because we are getting close to this, but let's see.
Are you gonna post solutions to the homework?
Yeah.
Awesome. That would be helpful.
So my intention, according to the syllabus, like for instance, this first set of homework, 1.2, now you're working on 1.3. Tomorrow we'll do 1.4, and then it's basically due shortly thereafter. It's July 15th, it's Thursday. So you're going to give it to me Thursday, and then I'm going to post the solutions for it the next day, because I really want you to grade your own. I want you to, as I said before, the goal is to fix your thinking. I don't need stuff to put in the grade book. The goal is just to fix your thinking. You also might notice at a glance, notice I don't assign a lot of homework. There's not like 20 questions in each section. There's very few. I would recommend, I'm doing that because exactly what I said today, I only gave you 2 questions, but if you're smart, you'll say, great, that gives me a bunch of other time to play around with a bunch of other problems and make sure I'm familiar with this and try to come up with something cool. It also gives you time to slow down and ask a lot of questions and really think. I would rather see you think about 5 questions than me to assign 20. I'd rather you think deeply and wonder and reason and try stuff and ask your own questions. What if I change this to this a little bit? Like slow down and think and really make sense of this stuff. So you should just be working on these first 3 sections as I teach them to you. And then once these are all done, then you're just going to scan, and I'll show you this right now. You're going to scan them all and send them to me, and then I'll post the solutions to them. What's that going to look like? Well, here in homework 1, notice it says, just like I said on syllabus, it's due Thursday, 7:15. I don't know if you've had a chance to do this yet, but if you click on that, what you're going to get is, well, nothing, because there's nothing in here. There's not an assignment sitting there. I didn't post the assignment there. It's in your book. But if you click on start, it says, do your work on paper. When finished, scan it as a PDF, upload it using the links below. If there are multiple pages, scan them, send so that they can be saved as a single document. You're going to do this on your test too. Basically, you're going to give me a PDF file, because I can open a PDF file with my iPad and grade it right on there and send it back to you with my comments and stuff on it. So, and if you haven't played with this before, you don't need to scan this on a computer. It's actually way easier to do on your phone. Whatever you're writing on with paper, you can, probably the best one is Cam Scanner. And we can talk about this during class. If you have trouble with this, we'll figure it out together, and probably you will be more help to each other than I will be helping you. But Cam Scanner is a free app that you can just use on your phone. If you have an iPhone, there's a note feature in it that already has the ability to scan built into it. And so you're going to scan that. And then if you click on first question, then you're just going to attach that file right here. And so that's how you're going to give me tests and homework. Does that make sense? Okay. Feels to me like we are done for today. So as usual, stay after if you want to play around with something, or if you have questions about yesterday's assignment, or maybe even today's upcoming assignment, things that you don't feel good about. Today we haven't, and this is never going to happen, that you get out of class early. I'm always going long. This is probably the first time it's happened in a year. So take advantage of it.
Thanks, Doug.
Good to see you all.
Hey, Doug, I have a quick question for you regarding the